Okay, so let us start. Let's see here. And today what I'm going to do is to discuss some basic martingales for the Brownian motion. And the plan is basically to start with, you know, some really down-to-earth things, and then for the one-dimensional Brownian motion, and then say a couple of words about multidimensional Brownian motion, which didn't appear yet, haven't appeared yet, and okay, it's not a very good thing that I still haven't introduced it. Okay, good. So what is the terminology? Yeah, I would prefer to say a reminder and just to say everything is already done in the course on martingales and Markov chains, which is not actually the case, but still is going. I mean, all the facts I'm going to use should appear there. So terminology reminder. As usual, let us assume that we have a filtration on our probability space. So we have some probability space, and the process xt goes this way, measurable with respect to the tensor product. We have some filtration. Which basically I don't think to be generated by this process. This is just some filtration. And I always will assume that it is complete, which means that okay, it's right continuous. And all the events of probability 0, I mean, all the events that are contained in some other event of probability 0 are also in our sigma algebra. So the measure is complete. And, okay. And, okay, P outer measure 0. Then this process is called a martingale with respect to this filtration. With respect to this filtration, if for any two times, for any s less than t, if you think about the conditional expectation of xt given fs, it is just xs. Two trivial remarks. First, you need your process to be integrable, right? Just to be able to write expectations and conditional expectations. So we need xt being an integrable random variable. And second, in particular, it implies that xs is measurable with respect to fs. Okay, just because the conditional expectations are. You can impose this condition from the very beginning, so that's what people typically do. And then yet another thing is our stopping times. So they already appeared even here. So this is a stopping, tau is a stopping time with respect to ft if for any given t the event tau less than t is in the sigma algebra ft. Okay. And then given a stopping time, also you can define the sigma algebra of everything that happens before tau. So just again, this already appeared in the discussion of the strong Markov property of the Brownian motion. So this is the set of all events A such that for any t, A cap t less than tau is measurable with respect to ft. Okay, that's just some notation if you wish. And then there are two important facts about Martingale's two theorems. If I need yet another notation, no, I don't think so. Two important theorems. So first, this is optional stop. And as far as I understand, it was discussed just this Monday, right, in the discrete setting when the filtration is, when the time is just z, not r. Again, for simplicity, let me assume that all the processes I'm dealing with are continuous, meaning that they have continuous trajectories almost surely. So if let us assume that all the processes are continuous. The reason for such an assumption is basically that we would like to have statements for all t's simultaneously for all the values of time, and this is an uncountable set, so it's very convenient to have a way to pass from, say, rationals to all the reals. And because of that, you can put here right continuous if you wish. The idea is just to be able to characterize the cool trajectory by a countable set of values. So if xt is a martingale, and say sigma and tau are two stopping times, then given sigma, let's take sigma, provided you have some uniform integrability. So again, think about the discrete situation. Discrete situation, you can basically check this statement step by step. Well, if tau is uniformly bounded, for instance, so you always know that you need only finite, say, 100 steps, then there are no problems with convergence. But in general, it could be. And you need some, basically, to apply some dominated convergence theorem. So provided there exists a random variable y with finite expectation such that for any t, okay, just for any t, this is less than 1. the role of this y is, you know, the upper bound to apply dominated convergence. Okay? If you by some reason, for instance, know that your martingale is uniformly bounded, okay, no problem, you just apply optional stopping and there is no condition to check. Good, then yet another notion, xt is called submartingale. If here you have not an identity where here, but you know, if xs is less than the conditional expectation. And in this case, I think, yeah, it's better to assume that xs is measurable with respect to fs. If and this inequality holds. Okay? So if this is an adapted process and you have such a bound. A standard source for submartingales is just some convex functions of martingales. So remark if we have a martingale and we apply to it some convex function, then this is a submartingale. The proof is basically trivial. This is Jensen inequality. In particular, you can just take the absolute value as f, or maybe the pth power of your process. Okay? And then the second quite important theorem is the maximal inequality by Doob due to loop. Which gives you control. I mean, this is, the most natural way to think about this result as a sort of a generalization of Chebyshev's inequality, which gives you a trivial bound for the probability that your random variable is big. So if xt is a submartingale, with continuous trajectories, let me continuous or right continuous trajectories, then for any, say, lambda, or maybe what do I need? Okay, let it be lambda here too. So for any lambda and any time, the probability that the maximum over 0t of xs is at least lambda is bounded from above by 1 over lambda expectation of xt, indicator of the event xt is actually greater than lambda 2. And Okay, this is just a general statement. And if xt is positive, then you can just forget about this, right? So then what you have is a straightforward generalization of Chebyshev. And moreover, you can, I mean, if you already know this, then you can deduce a bound in LP spaces, which says that the expectation of this maximum power p 1 over p is less than p over p minus 1 expectation xtp 1 over p itself for any p greater than 1. So here, I mean, the meaningful case is when you know that xt is in some LP, right? So if you just know that this random variable is in L1, this could be infinity. Well, the meaningful situation is when you say no that xt is square integrable or something like that. So, okay. Let me comment here. Provided otherwise, you just have an infinity, the infinity. And yet another remark. If you know that xt is a Martingale, not necessarily positive, then, as I already mentioned, then this is a submartingale. And you can apply the last bound. So, this is a question? No?
I don't know, it's a stupid question, but I'm trying to put p equal to infinity. Can't manage to.
Well, then,
Maximum is less than.
this is basically what's that? This is the maximum value which this maximum can attain, right?
Yes. Yeah.
And this is the maximal value that xt attains. And what we are saying is that if it happened that xt attained some whatever level, if it reached level 100 in the middle, then the trajectory is such that it is still above 100 at the very end.
No, there are not such trajectories that there are above, because maximum is less than.
Well, okay, so for the infinity, this is essentially maximum over the probability space, right? Well, supremum, if you wish, of the probability space of this maximum. And then what we are saying is that this is less than the supremum over probability space I mean, except sets of zero measure of maximum xt, which seems to be correct, right? So just because of the Martingale property. So if it happened that with a positive probability we are above level 100 at least one time, then with positive probability we are above the level 100 at the end of the day. Okay, good. And it was some terminology. Then what are the basic martingales? So let Bt be a standard Brownian motion. Then, well, it is itself a martingale. Bt squared minus t is also a martingale. Moreover, you can take any positive lambda, okay, this is some other lambda than there, and write what's called the exponential martingale. The proof is basically, extremely straightforward. You just compute something with Gaussian random variables, so it cannot be a deep statement, right? I mean, so it should be a straightforward check. So for Bt, this is obvious. For Bt squared, so this is trivial. For Bt squared, you write something like this. What do we need? Square plus. Yes, this is just an identity, quite trivial identity. And then when you take expectations, here you see the random variable, so the expectation is t minus s. And here the expectation cancels the expectation, conditional expectation with respect to fs, just because this increment is independent of fs. Okay. So basically you are done. And for B, again, so this is pretty straightforward. Well, basically what you need to compute is this expectation, right? To prove that what we need is the expectation of something, some xt fs xs, where x is this exponential. So you just take two terms, lambda bs minus lambda squared s is a multiple which is independent of fs, which is measurable with respect to fs. So it's just here. And here again the increment is independent. And basically this is a straightforward computation with the Gaussian variable. That this expectation is 1. Yeah. Good. Now let me just discuss a bit what is the link between B and A. Okay, that's what you see in all the courses, I mean, that there are such martingales. So the link actually is rather straightforward, so remark. Oh, I need more space. Let me erase everything here. So some remark. We know that this is a martingale for any given lambda. Okay? Let us take the Taylor expansion of this with respect to lambda and check what happens. Then, well, what I would like to say is basically the following. So if I know that this is a martingale for any given lambda, and I see that if lambda is very small, then bt is the leading term, it should be a way, okay, some technicalities are probably involved, but it should be a way to interchange the notions, right? So if I know that this is a martingale for any lambda, then I know that this is a martingale for any, yeah. Right? I mean, okay, you should interchange the limit and the expectation. Well, imagine that there is some uniform bound. But once I know this is a martingale, I can subtract it and conclude in the same way that this is a martingale, etc. So what I see is the whole series of polynomial martingales. And if you are familiar with what Hermite polynomials are, these are exactly here. Okay, so in fact, it's just the sum of what I would denote H tilde and this is a version of Hermite polynomials. Well, the true ones are, well, here. And they are given by differentiating, so you can obtain them just by differentiating the exponential and maybe there is a sign also, plus minus. So this is the definition you might see in your calculus class. So what we have here is more or less just stretched version. So instead of x, you take x over square root of 2 or something like that. No, it does not fit. Okay, 2 minus n over 2. Okay, now it's better. Something of this style. But anyway, just to mention this idea that if you have a family of martingales, then in general, I mean, if you have some uniform convergence or something like that, in general you can differentiate with respect to the parameter, and then to see some other martingales. And well, okay, it was remark A. And remark B, which is much more important. One can ask the inverse question. So what should we know about our process to claim that it is a standard Brownian motion? Again, you can imagine that if you have a whole collection, I mean, a really huge collection of martingales, probably it should be enough, right? Because like the physical analogy is that you have many, many conservation laws, and they are enough to, to fully characterize the behavior of your system. Okay, so it is not very surprising, for instance, it would not be very surprising that the whole family, say, of these martingales characterize the Brownian motion, because you have a lot of information. A deep fact, which is another theorem due to Levy, is that actually it is enough to consider only the first two. So if xt with continuous trajectories has continuous trajectories and both x and c squared minus t are martingales, then this is a standard Brownian motion. This is not for now. I mean, this is a deep result. Hopefully we will discuss it. So. But again, so a weaker result could be that, you know, the family of martingales characterize everything. The deep is only the fact that we need to. The deepness is in this fact. Again, good. Now some simple applications of the optional stopping that I'm just erasing. Well, say proposition. Let tau be the infimum of, be the heating time of one of the 2 points, minus A or B. These two are positive. So what you do, you just take two levels, just consider two levels. One is here, the other is there, and take the first time you hit one of them. See here, this is tau. Then, first what we know is that it happens almost surely, right? So we hit one of these levels, and then the question is what are the relative probabilities? And the answer is fairly easy to guess. And B, if I take the expectation of tau, what's that? Is there any way to compute it just in a second? Well, actually there is, so this is the proof. Well, okay, this is AB. Again, this is a very, very basic computation with the Brownian motion. How it works, say in A, what you do, you just apply optional stopping to this time tau. Until tau, everything is uniformly bounded. So we have no headache about this dominated convergence, right? So this process, I mean B tau minimum t, is just bounded by A or B. So, okay, apply optional stopping. Uniform. And then what you see is that B probability we end above minus A probability we end below is what? This is just the expectation of what should I say? This is just the expectation of B tau, right? And because of the Martingale property, this is B naught, which is 0. I hope it works, right? So we know the relative probabilities, and the sum must be 1. Question? Nope. And for B, what you do, well, the trivial idea is apply optional stopping to the other Martingale, to this guy. If it works, then what we see is, okay, what is the expectation of B tau squared? The expectation of B tau squared is B A squared plus, okay, minus A squared if you wish, plus AB squared minus the expectation of tau. Right? And it gives you the formula. There is some problem. So the problem is that, in fact, we do not know that this is bounded, right? And this is an essential condition in the optional stopping. So for instance, imagine the stopping time, which is the first time you hit the level -1. Your Brownian motion hits -1. Okay, this is a proper stopping time, and at this time, the mean value is -1. Which is not 0, I mean. So it should be some condition. And to handle this, what you do is consider first the process B tau minimum something fixed, say T capital. Consider a truncated process. So you declare that now your stopping time is not tau, but the minimum of tau and 1 million. Okay? And then apply optional stopping to this stopping time. And well, what you see is that the expectation of this new stopping time is the expectation of this B squared at this moment, which is A squared probability we ended where we ended below, plus B squared probability we ended above, plus some contribution of the event that we are still in this strip. Okay? In this case, B is uniformly bounded, so what you have is just O capital of the probability, some constant probability of the event that we are still running in this strip. And then you just pass to the limit as t goes to infinity. So as t goes to infinity, this probability converges to the probability that b tau is minus a, this converges to b tau b, and this tends to 0. So what you basically have, okay, is what we need. And the left-hand side tends to the expectation of tau just because of the monotone convergence. Because now tau minimum t is a monotonely increasing sequence of functions on your probability space. Okay? Good. Now let me make yet another remark. Yeah?
If you in advance that expectation of tau is finite, then we could apply it straightforwardly?
Nope.
Do we need to know that?
Well, you need to know that. No, you need to know. So, okay, it's positive. You need to know. Oh, okay. So okay, yeah. You can. Well, in this case, yes, one can apply this straightforwardly because the random variable which makes the dominated convergence working is now tau plus some constant. Okay, so it was some variable y, I don't remember where, and then you just take tau plus whatever b squared as your dominating random variable.
So once we know that the expectation of tau is finite,
right?
It would work.
Yeah, it would work. Just because you can take this as as the uniform bound at all the times. Okay, is it clear for everybody what was discussed? I mean, if we would know that this is finite, we just take exactly this variable as y. Okay, good. Now, yet another remark. Well, actually, I need to make at least two. So, okay, the first is about the situation we have just one level. So instead of 2, we just have whatever, minus a. And what okay. What we would like is to say something about this stopping time. Now, tau minus a be the infimum of all times we are on this level. Oh, la, 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 la. It should be the other way around. Let this level be above. Sorry for this. Everything is symmetric, so. Well, okay, let it be above. And here is plus. So we just have one bound. And well, I would like to say something meaningful about this time. In particular, I'm wondering if it has a finite expectation. So this is exactly your question. So, okay, what should I do? Just consider this with some lambda positive. By the way, I didn't say that, oh, okay, I said here that it's for lambda positive, but in principle it's not needed, right? So you can also play with other values of lambda. So Here, the restriction we have positive lambda is basically for nothing. Okay, just consider this object. And until time tau, nothing bad happens. Why? Because this is just negative, so it decreases the value, and BT is bounded from above. So we can apply optional stopping. Okay? So note that this is less than what it is, A. And positive. So optional stopping just gives us what? That the expectation of the exponential of lambda A minus lambda squared to tau is 1. Right? So, in other words, the expectation of mu tau A, where mu is what is square root of lambda squared over 2 is now mu. So lambda is square root of 2 mu. Okay? For any positive mu. This is called the Laplace transform. Of the probability density of mu. What is the message here? So imagine for some random variable, you know its Laplace transform. Then there is a way to recover its mean, its second moment, etc., just by differentiating. Okay? So the expectation of this positive random variable should be just the derivative of 0 with another minus because of minus here. Just imagine that you differentiate this with respect to mu. What you have is tau in front, right? And when you then substitute mu 0, everything cancels. Okay? It's not differentiable. Well, this is slightly informal, of course, so the formal reasoning is the other way around. So assume that we have a finite expectation, then it must be differentiable, which is not the case. Okay? So the message is that if we have just one bound, then this expectation is infinite. And in particular, it means that it is a bad idea to apply optional stopping just to this guy. We are going to have some nonsense. It's clear what happened? Okay, good. Then let us make a break and continue after that. Yes?
So for example, if you take a Brownian bridge starting at 0,
right.
And you can compute with optional stopping the expectation of
This is not a Markov process, right? I mean, so well, I think that it's computable, but not in this way. Not in this way. So Brownian bridge is not a Markov process because we have an information from the future that we are going to land here. So let us continue with the second. Is it okay with the sound? Yeah. Let us continue with the second remark. Now, recall sort of a discussion we had last time about down crossings. what I'm now interested in is the following question. So, So here there are two levels, B minus A. And then there is this Brownian motion. So let me take the first time it hits B, for instance. It was last time called sigma 1 or something like that. And what I'm interested is the time it spends in this strip before it hits level minus A. So this is the expectation of the measure of times t greater than sigma say sigma 1. This is hitting of B such that t in sigma 1 tau 1 such that this is next hitting minus A such that BT is inside of this strip. This is basically the answer to your question last time, why it was a proper normalization. So, how should I think about this? There is a simple claim which works as follows. So, again, imagine that here there is yet another peak, for instance. Just imagine the following procedure. You take all the excursions that are above level B and just throw them out. The claim is that what you have when you just cut all these pieces out is the reflected Brownian motion. So because of that, I can rephrase my question in terms of the reflected Brownian motion. So just to say that this is the expectation of the time tau, where what is tau? Tau by definition is the infimum over all times such that BT is A plus B. And this is going to be in exercises, which I still not typed. Yet again, what happened? So what I'm doing, I'm just deleting all the pieces of my trajectory which are above B. So what I have after that is something like that. Oops. Now the claim is that it's distributed exactly in the same way as, after the first hit in time, is distributed exactly in the same way as B minus BT. Yeah, this trajectory. And then the time when I hit the level minus A is exactly the time when this BT hits A plus B. Okay? And all these excursions, they do not contribute to the yellow time here, and they're just not drawn there. Okay? And because of B, we just know this expectation. This is A plus B squared. And then recall the formula I wrote for the local time at 0. It was limit over shrinking intervals of this by the number of crossings. So what's going on with this formula? So basically we know that if we hit the level B next time, then the time we are going to spend in this strip has a mean a plus b squared. Okay? So what I'm saying is that the mean time spent in minus AB during down crossings is roughly what? Just the number of these down crossings by NBN by AN plus BN squared. Okay? Since each time, on each of them, I spent roughly a plus b squared. Then, just the whole time is twice larger, well, conjecturally. Why? Because we expect the down crossings contribute more or less the same amount of time as up crossings, right? So there are several pieces of trajectories here in this strip. So some come from downwards passages, and the others, like this, comes from the upwards. Well, okay, now this is the whole time spent in this strip, and what we also should do is to normalize it by the length of this interval, because what we are interested is essentially the density of, this time spent in the strip at 0. So we normalize by another a plus b, and this is the reason why it seems to be a proper normalization. Okay. Are there any questions? Again, so the idea here is just to illustrate that many explicit computations are available for the Brownian motion. So you can compute this and that and make some conclusions, just playing with some martingales. And maybe with reflection principles with statements of this sort. Yeah. Good. Perfect. And now, this is a sort of another story, though not very far. Sort of intermezzo. Multidimensional Brownian motion. Okay, so first, what's that? Let BT1, etc., BTD be independent Brownian motions. Then I just consider the process which takes value in RD. So basically, each of the coordinates fluctuates independently. So RD is called d-dimensional Okay, this moment, nothing very deep. Well, you can think about, say, path properties properties of these trajectories. Say, what is the smoothness? I mean, what is the optimal Hölder exponent? The answer is, of course, this is the same as for one-dimensional. This is boring. So you can think about if it satisfies the Markov property, if the strong Markov property holds. So for the weak one, this is just a trivial statement. For the strong one, okay, this is also not extremely deep. You just mimic the proof for the one-dimensional case. And so remark is that all these holds. Strong Markov. Good. Now there is another quite simple statement about d-dimensional Brownian motion. So this is closer now to the real movements of particles, right? So because in RD we have more symmetries, so we can say rotate the whole space. And the trivial lemma is that, okay, if this is a d-dimensional Brownian motion and this is some orthogonal transform, well, isometry, if you wish. Isometry keeping the origin, I mean, the origin. Then this is distributed in the same way. And the corollary of this fact is the following. So if P, okay, which may be not a very good name, T is an orthogonal projection on some less dimensional space, then this process is a Brownian motion in T. Okay, T is also not a TRD. T is also not a good notation. But, okay, let us live with this. So why this is true? Again, there is absolutely nothing deep here. So just think about one increment, just the increment from the time 0 to time t. This is a Gaussian normal. This is a Gaussian random variable in RD. Well, it's centered and it has a covariance matrix, which is basically identity, proportional to the identity. This covariance matrix is, of course, invariant under all possible rotations. So when you rotate, what you have is the same distribution. Okay? So just check that all finite dimensional distributions are the same. So what we need, voila, is something like that. So this is question. This is B. And you proceed in a very standard way, so you just consider increments. So you just say that these are independent. And for each of the increments, bless you, you have this rotation symmetry. I mean, really is sort of a boring statement. Though it tells us something, right? In particular, this is for A. And in particular, it says, okay, if I start with this construction, so if I choose my preferred orthonormal basis in RD, and just run independent Brownian motions in this basis as coordinates. And after that, I project onto some other space. Then I still have a Brownian motion. Okay? So for B, just, trivial if T is a coordinate projection. And one can always apply A in the general case. To make this projection, to make this subspace to be a coordinates subspace. Okay. Hopefully there are no questions so far, but if there are, please ask. So now what I'm going to discuss is what are the martingales. So a sort of a discussion. Maybe do it here. So what are the martingales for multidimensional Brownian motion? Are there any suggestions? Do you know any martingale? For multidimensional. And let me think about martingales that do not involve time. Okay? Well, of course, one can take the first coordinate. Trivial. What can we do on the next level? I mean, if I would like to have some quadratic polynomials of coordinates, what are the martingales? Well, I claim that this is a martingale. Is it clear why? Just because I have a product of two independent variables, basically, right? B1 and B2 are independent of each other. So the conditional expectation of the first is BS1, the conditional expectation of the second is BS2. Good. Also, this is a martingale. Just because, okay, if I subtract and add t squared, then I'm done. Okay? Well, there are probably more, but let us try to be more general. So, more generally, for any collection lambda 1, lambda d, such that the sum of squares is 0, So it was actually my fault that I wrote lambda positive in that property, and it is not needed for the proof. So here what I'm doing is I consider complex valued lambda. Okay? What should I write here? This is a martingale just because, again, this is a product of something that depends only on the first coordinate, only on the second coordinate, etc. Okay? By the way, note that these two are related to each other by rotation. This is the same quadratic form. So this is the product of x and y, and this is the product of these two coordinates. Okay, good. So here it should be t. I do not need this condition, I mean, to claim that the product of martingales is a martingale. But if I have this condition, then what I know is that the t terms cancel out. And what I have is just such an exponential. Mm-hmm. Now I can play the same trick. So let me fix some, I don't know, positive parameter. Let it be called lambda as well. So, and let me rewrite everything in this way. So, okay, now I have a function, of this parameter lambda, and I can play the same game I played in the one-dimensional setup. I can think about what are the terms corresponding to lambda squared, etc. Okay? So the claim is that if I have, well, for any collection of parameters with sum of squares being 0, just the power of this sum is a martingale. And now the question is, what is special? I mean, these objects are just polynomials in coordinates, right? So the first two in the case d equals 2 are written here. So you just check in the case if d equals 2 and equals 2, then basically the only non-trivial solution to alpha 1 squared plus alpha 2 squared is 0. You take one of them 1, the other I, and then what you see is that you have b1 plus e2 squared, which reproduces you to two quadratic guys already written. Okay, so now what I'm asking is what is special in these polynomials. So just think about them as functions of several coordinates. And if you think for a second, then the answer is basically trivial. These polynomials are harmonic polynomials. So, okay. Note that if P of X, this is in Rg, is written in this form, then the Laplacian of P is 0. Trivial computation. Just differentiate, and what you gain is alpha 1 when you first time differentiate, and another alpha 1 second time. Okay? But then somehow you can change the perspective. So the first question you can ask is the following, okay? I have many polynomials with some restriction. Do they generate the whole set of harmonic polynomials? As far as I understand, this is the case. So any homogeneous harmonic polynomial of degree n is a linear combination of such guys. Well, the sketch of the proof, just compute dimensions. Do you follow? I mean, so I use this notion of harmonic polynomials, you know, as everybody knows what they are. I mean, they're just polynomials in variables that which satisfy Laplacian equals to 0. So proof, of course, this is a linear space. If we fix the number of variables and we fix the degree, this is trivially just a finite dimensional linear space. Compute dimension. It should be number of monomials of degree n minus number of monomials degree n minus 2 in both cases. So, okay, what we have right now. So right now we see that basically for any p polynomial such that, okay, it's harmonic, the function p of bt is a Martingale with respect to bt. Okay, it's Martingale. Yet again, why? Just think about this simple example when both dimension and the degree are 2. So we know that this is a Martingale and that is a Martingale, and we know that there are no other. There are no other harmonic polynomials. So each linear combination of them is again a Martingale. Now we do exactly the same trick in the general case. Okay, so we know that whatever harmonic polynomial we have, we can find a representation of these harmonic polynomials as a linear combination of powers. And for powers, we know that they are Martingales just because of this trivial computation. Okay?
Could you please comment on how we pass from exponent to
To here?
Yeah.
Well, that's again the same trick. So what I do is Taylor expansion and this single parameter.
I mean, we need to somehow interchange.
We need to interchange it, yes, and this is exactly the detail I'm not discussing here. This is a very good question here. Yeah. I mean, we need somehow to interchange, so we need to know the uniform bound on tails. Why it works? Just because the density of Gaussian variables decreases super exponentially. So yeah, that's a fair question, and the fair answer is that yeah, I didn't say anything on this. Okay. So that's more like a motivating discussion. I mean, you can imagine also that for any polynomial, whatever, if you have a polynomial, this is a straightforward check. So this is more like a discussion of structure of the space of all martingales. Okay, so okay, this is a martingale. But then you can make another jump. So, and to say, okay, it's tempting to say, and this is indeed true, to say that h of bt is a martingale just for any harmonic function. Well, again, you can actually prove it. Why? Because harmonic functions, they are very nice. They are real analytic. So in the neighborhood of a given point, you know that your function has a representation as a Taylor series, right, in many variables. And each of the components, the component of a given degree, must be a harmonic polynomial. So we know that each of the components is a martingale, and we know that there is a uniform convergence. And again, okay, you play with some estimates if you wish, and you can prove this fact. So this is not like a very big cheating. Good, but then, okay, now many questions arise. So first, we actually know that harmonic functions in dimension 2, for instance, are invariant under a much larger group of transforms, so pseudo group of transforms, than just rotations. Okay? They're invariant under all conformal transforms. And because of that, you can expect that actually in the special dimension 2, again, if we believe that such a huge family of martingales essentially define the trajectory of the Brownian motion. So time is not involved now, but okay, define it maybe up to time reparametrization. Then you should expect that actually these trajectories are conformally invariant because the property of a function to be harmonic is invariant under conformal maps. And the way how I have written this on the blackboard is morally algebraic, right? I mean, so we start just with the very simple observation. And then what we see is this huge conclusion or conjecture or whatever. Good. And okay, let me now spend some time in another form of this invariance under conformal mappings, another form of this statement about martingales. So just link between the multidimensional Brownian motion and Dirichlet problem for harmonic functions. So, what is the Dirichlet problem for harmonic function? Imagine you have some open subset in Rd, and you have some function defined on its boundary, okay, which you supposed to be relatively nice, say, continuous. So what you want is a function h defined in the closure of U such that it is harmonic inside and well, continuous in the closure. I mean, so it has fair boundary values. Okay, continuous U, and such that on the boundary this is phi. Just has prescribed values. Yeah, this is what's called Dirichlet problem for harmonic functions. Then, okay, the question is, well, how to solve it, how to prove the solution exists, etc. And basically, this is the question from the course in PDEs. But what I'm going to say is that there is a very natural link with the Brownian motion. I mean that you can solve this problem. So this was the Dirichlet problem. Just thinking about some probabilities. Okay, to formulate the result, what I need is another definition. So boundary point is called regular boundary point. And now I need some notation, so some additional notation. Now what I'm going to consider a Brownian motion started not at the origin but at some other point. This point I'm going to write here as a subscript. So this means we consider the M started not. If the probability was BC. So if almost surely this sigma is 0, so what sigma is? Such that dt is not mu. So what's going on? You have a boundary. It could be quite complicated. For instance, a single point or maybe some dust of isolated points. And then you say, I'm here. And I just start my Brownian motion from this point. And I ask myself if it immediately exits the set or not. So imagine that there might be some troubles, for instance, if you just think about the an isolated point inside. Then it exits and it seems that it never comes back. Okay, so this is just a definition. And a sort of a remark, 0-1 law implies that this probability is actually either 1 or 0. This is the event that fits into the sigma algebra F0 plus. Okay. So this is a definition. And then there is a theorem. So let we have a bounded domain such that all boundary points are regular. Then the Dirichlet problem basically can be written as an expectation of something, and what's this something is given by H1, the expectation of phi b be what? I think this is correct. So what's going on? Again, imagine you have some domain. Nope. Okay, it's strange. It's still yellow on sides, but white there. Okay, so you have some domain. So here is the point y. You start the Brownian motion from this point. Wait until it hits the boundary and take the value, so this is b sigma u, and take the value of phi at this point. Okay, so here is the claim. It seems that I have no time to prove it because there is some, well, okay, I need 10 minutes for this and I do not have it. Let me just make a comment. On this theorem, so which I'm going to prove next time, by the way, to be complete. So what is the comment? You can think about this theorem in the very same spirit with the discussion above. So that it's tempting to say that all the harmonic functions of the Brownian motion are martingales. So why? Just think about some stopping time. Think about geometric stopping times for BT. What do I mean? Just imagine that you have a smaller domain, for instance. Here there is some u prime, and you consider the time you first exits this u prime. Then, okay, let L prime first exit from some subdomain. Then what we have is that h of whatever b, okay, h of y is just the expectation, if we start at y, of h of b tau prime, right? Because you can apply the same theorem in the yellow domain now, and the boundary values are given by h itself. Okay, so here the boundary values are given by phi, and here they are already given by h. So what you see is basically that for this stop in time and for this function, h of b is indeed a martingale. Okay? So this is just a source of harmonic functions, and well, provided we believe this is true, so it works. Well, I think that's it for today. Yeah. It's a good place to stop. And maybe yet another comment here. Yeah, sorry. So what's going to be after this discussion? So good. I mean, what's the impression you might have now? The impression is that probably we need a sort of a calculus to work with such objects. Like imagine in a smooth setting, so we perfectly know how to compose functions. So if we have a differentiable function and we compose it with something else, we know everything about the composition. So because there is a chain rule, so we know it's again differentiable, we know what the derivative is. And here it seems that things are, well, a bit tricky. So, and to handle such questions freely, so what we actually need is an analog of this calculus, I mean of the ordinary calculus, for the Brownian motion, for diffusions. Well, this is what we will discuss in remaining lectures. Yeah, that's the plan. Okay, that's it.